Hi, hello everyone. Welcome back to Deep Learning video lecture series. This is Dr. Chiranjeevi Manike, Professor in Data Science and Cybersecurity Department, MLR Institute of Technology, Hyderabad. And in this lecture, we are going to discuss challenges with the gradient descent. So mainly, we are going to cover the local minima and saddle points. What are these concepts, and what is mainly the two other important concepts: vanishing gradient and exploding gradient. So in the previous lecture we already discussed how a loss function, what is a loss function, how the error of the loss function is related to the weights and biases, how the training happens in deep neural networks. So now, and we already discussed about the gradient and what is the bias and what is the impact of learning rate and all these concepts. So now there are some challenges with the gradient. Let us try to understand what are those challenges, so that the next lecture there we are going to discuss the types of gradient descent algorithms. So there we will understand. So the first challenge with the gradients is a local minima and the saddle points here. So what is this local minima? What do you mean by this a saddle point? So if you look at the convex problem, that is where the convex problem is a mathematical problem where the objective function and the constraints are convex. So that means they have a bowl shaped curve, so which guarantees that any local minima is also a global minima. So which makes it easier to find the optimal solution. So from this you can see, and this is a bowl shaped curve, and this is a non-convex. And let us also understand what do you mean by this a non-convex problem. So a non-convex problem is one where the objective function or constraints are not convex. So that is potentially having a multiple local minimas, you can see, and this is one local minima and this is one local minima, this may be, and this like. So it have multiple local minimas, and that's why it is more difficult to find the two global minimum. For convex problems, the gradient descent can find the global minima very easily, but as non-convex problems where we have many local minimas, as a convex problems emerge, the gradient descent can struggle to find out the global minimum. So where the model achieves the best results. Here you can see this convex problems, how the gradient descent, like suppose if you have initialized the gradient descent value, and this is the way the gradient descent works, and that is to reach the optimal solution. And whereas the non-gradient algorithm that may overshoot the optimal solution, that is a global minimum. And from this non-convex function, that is we can represent in the form of a 2D space. Here you can see we have the different local minimas. So the gradient descent and the initialization point at this point. So here, and this is a one local minima, and this is a global minimum. So local minima mimic the shape of a global minima. So where the slope of the cost function increases on either side of the current point. The saddle points, that is with the saddle points, the negative gradient only exists on one side of the point. So that is reaching a local maxima on one side and local minima on the other side. So that is a problem with the local minima and the global minimas. That is mainly the saddle point also. And here you can see the animation, that is to show how the gradient descent works because of the presence of the saddle points, how it is going to affect. So let us take the learning rate as a 0.4 and the starting point as minus that is 0.5, and let us observe the each step how the gradient is moving from the starting point here. So because of this presence of the saddle point, now here you can see the gradient moved to here and it overshoot, and then it from this it has moved directly to this point and then oscillating here, and again it goes back and this, and from this again it is starting. Okay, so that is, but we are not going to discuss in detail, but while discussing mathematical, that is in detail mathematics about all, and we will understand much deeper, that is in advanced course. Next, another very important is a vanishing and a exploding gradients. So what is a vanishing gradient? What is a exploding gradients? So as we discussed, based on the loss function, in order to minimize the loss function, because the objective is to minimize the loss function so that we expect the model to perform more accurately. So that error information will be propagated from the output layer all the way down to the input layer. So here in this process, that means the propagating, that is like error, the gradient descent algorithms, if you go back to how the gradient descent algorithms works, and this how this error information will be propagated back from the output layer to the input layer, that is what amount of the weight need to be adjusted, what amount of bias need to be adjusted. So this how we are going to decide, that is decided by the gradient. So when the vanishing gradient problem occurs, so we have to understand it, because when here, and if you take a curve like this, suppose if you have started at this point and with some learning rate, and the gradient descent works like taking the steps like this and to reach the optimal. So that means, and if you recall the equation, that is to update the very basic how the weight would be updated. So the weight, this is a new weight and this is old weight minus learning rate and this gradient. So the gradient of theta. Okay, so this is a gradient, and this is learning rate. This is old weight. So this is the way, by using this gradient we update the previous weight. So here you can observe the minus, that means, and this is the point we have started, and this is the point where the optimal solution is exist. So if you, this is a slope, that is a gradient is nothing but a slope in which direction we have to move in order to reach the optimal solution. So we have to move in the reverse direction, that's why we have to subtract this gradient. So that means it becomes small and small in every layer, like from one layer to another layer, that is our one step to another step in the backward propagation. So that means it becomes small and small and small. So once it equals like 0, let us say if the gradient becomes 0, so that means this will become 0. So then previous weight and the current weight would be same. So if previous weight and current weight remains the same, then there will be no learning. So that is called as a vanishing gradient problem. That is, gradient is becoming small and small and small when we propagate this gradient, that is from that is output layer to input layer. So that is gradient is becomes too small, this vanishing gradient. And next one is a exploding gradient. Exploding means the gradient becomes too big, too large. So then the model becomes unstable. It will not converge, will not also learn, and so this is another problem. But we have some approaches that is to overcome this problem, like vanishing gradients and also the exploiting gradients. Those will be discussed in the coming lectures. So in this lecture we discuss mainly what is mainly the challenges in gradient descent algorithm. The major challenge is local minima, that is mainly we discussed like a convex and non-convex functions, and the saddle point, how it is going to affect the gradient descent algorithm. And another the important one is a vanishing gradient and the exploding gradient. Exploding gradients. So a vanishing gradient means when the gradient becomes small and small, that is, and whereas exploding gradient, the gradient becomes large.